All right, welcome everyone. Hi, Giovanni. Welcome to our Green Chemistry Commitment Info session. I hope you're all doing great. I hope you're all having a great day and and enjoying this Wednesday. Today we have a very special guest. I'm just gonna share my screen so you can see um a little bit of some slides. So hopefully you can see my slides and everything's going well. So yes, welcome again. My name is Juliana. I'm a program manager at Beyond Benign. Today here we also have our Monica Hensley. She's a content manager, also part of the higher ed program.
Jude,
And hi, sorry.
you have a Zoom pop-up on your screen, and also it's sharing with the notes. I think you
Oh,
need
thank
to
you.
swap your swap.
There you go. Is it better?
And you still have
Let
the
me.
pop-up message
There you
there.
go. Thank you, Monica. Okay, there you go. Thank you, Monica, for this. Uh, Technology is failing me today and all of us, but let's go. The meeting today is being recorded, and we're gonna send you all of the information after this meeting. So documents, slides, and resources will be available to you. And also, without further ado, I'd like to introduce you to our featured speaker. This is Dr. Glenn Hurst. He's a professor of green chemistry education at the University of York, and he's an amazing human being. So Glenn completed his PhD from Newcastle University. He was appointed as associate lecturer in chemistry at the University of York in 2014, and he was made full professor in 2023. He is the chair of board of studies, where he oversees the operation management, and he reviews the portfolio of programs and related learning and teaching provision in chemistry. Glenn, he specializes in adopting systems thinking approaches within all levels of green and sustainable chemistry education. And he also uses social media for technology enhanced learning and developing new mobile applications for game-based learning. And also in terms of awards, Glenn, he was one of the top 10 social media superstars in higher education 2017. He was a finalist in the Times Higher Education Most Innovative Teacher of the Year category, and he was also awarded the ACS Committee on Environmental Improvement Award for incorporation of sustainability into chemistry education in 2019, and also the RSC, the Royal Society of Chemistry Higher Education Teaching Award in 2020. So with all of this, I'm gonna stop sharing, change slides so I can go to Glenn's slides so he can continue his presentation. So just give me one time.
I
And
might actually be able to share my own screen. Can I have
oh
a little?
yeah, let's
Yeah,
try.
let's see. Someone else is sharing. How does that look?
That looks perfect. We did it.
Okay. Thanks so much, Juliana, and the whole Beyond Benign team for inviting me to speak today. I'm honored and privileged, and thanks so much for your very kind introduction. I really appreciate it. So today, what I'm going to be talking about is how Beyond Benign has really helped me as an individual, but also our wider department to facilitate both student partnerships between other students and staff, but also staff partnerships as well. Given that, and actually through making such partnerships to be able to develop and integrate more comprehensively green chemistry within our curriculum. And my approach to doing this, as Juliana mentioned, is very much by utilizing something called systems thinking. And you can see from this graphic on the right-hand side there, various work streams where we've attempted to integrate green and sustainable chemistry into the curricula through using this so-called systems-based approach. So why are we doing this? What's the big motivation for us? For us, training the next generation of scientists, engineers, and policymakers to solve the big global challenges is really what's driving us as a department, as an and as an institution. And these are outlined via the United Nations Sustainable Development Goals. So you can see these 17 goals here that relate to the big problems facing our planet at the moment. And they aren't isolated issues, and they probably aren't going to be solved by people working within silos or within one discipline, but rather they are interconnected, they're interdisciplinary, and they're going to be solved by diverse teams working together, considering entire systems and problems holistically and thinking about lateral ways to be able to solve them. And as I mentioned, using something called a systems-based approach helps us to achieve this and helps students as educators think about being able to visualize the links between different subject matter, and through that be able to build up a complex picture with various stakeholders and actors so that you can predict perhaps how outputs might change when the system is perturbed or when inputs change, or maybe even think about systems in a dynamic way and how they might change over time. So from a pedagogic perspective, I want to use this approach to help move people away from thinking in silos in a fragmented and reductionist way to one that's more integrated and lateral. And certainly green chemistry lends itself to systems thinking particularly well, because the 12 principles of green chemistry or life cycle assessment all depend on the reliance of reactions and processes on one another with local and global systems. So if you take a particular process, we might make a green intervention, might lower the temperature of that reaction. Okay, that's great. That's a green intervention, perhaps. But it's no good if it's a very wasteful reaction, if it's a very toxic reaction, for example. So we have to think of the big picture. And that's very much what systems thinking is all about. So what are the drivers for change from my perspective within my department, the Department of Chemistry at York? Well, very much changes in what our learned societies require for, say, accreditation, from my perspective, has been a big driver for change. So the Royal Society of Chemistry, they have bespoke accreditation criteria. I understand the American Chemical Society has a similar professional standards type framework. In order for us in the UK to be accredited, for our degree programs to be accredited, we now, as a requirement from this year, have to integrate green chemistry into the curricula. So that's a really powerful license and trigger to be able to get things started. Similarly, we're starting to see more and more legislation coming through, such that in order to be compliant from a regulatory perspective, we have to make changes in our curriculum. So we can imagine most recently, for example, changes in terms of which chemicals we're able to use. So dichloromethane, for example, is one solvent that is receiving particular attention at the moment, especially in the US. And we should be reactive as an education institution to adapt our curriculum such that we don't use chemicals that are significantly restricted, okay? And so that can also serve as an impetus to make changes within our curriculum. There's also been, at least in the UK, numerous reports where various societies and organizations have done an industry needs analysis. And as we mentioned previously, in order to equip the next generation to solve the big global challenges, we have to make sure that the future workforce, say within the process industry, chemical companies, have the necessary training and skills to evoke change, to be able to move us, for example, towards net zero. So what employers want by way of sustainability, by way of training our undergraduate students and graduate students with the skills to be able to use and implement green chemistry for the betterment, is another big driver. And actually, what we have found, certainly within chemistry at York, is that the students themselves are also driving change. They want this. They want to learn about green and sustainable chemistry. They typically ask us questions. Well, Glenn, do we have to use so much product in the lab? Does this have to be done at such high temperature? What happens to this product at the end? Okay, so that's quite a powerful driver for us to be able to enable us to integrate green chemistry into our curricula, be it undergraduate or postgraduate. And certainly one way that has also helped us, and I'll try to illustrate this throughout this talk, is by us signing the green chemistry commitment by Beyond Benign. This has very much acted as our harpoon, if you like, to move away from, in our case, we were quite lucky in the sense that we already had a fair bit of green chemistry within our curriculum. But since doing this, since signing the green chemistry commitment, even for an institution like ours, where we were doing quite a bit already, we have witnessed a really rather fascinating effect whereby it's galvanized the workforce and our students to want to do more in a coordinated fashion, such that academic colleagues that perhaps wouldn't consider themselves green chemists even are looking to adapt the curriculum accordingly because of signing the green chemistry commitment. So I have experienced at York Chemistry, since signing, we've moved away from an individual or a collection of individuals that might be doing green chemistry research, wanting to infuse it into curricula, to a much more coordinated effort where we're working in true partnership with one another. And so I'm going to try to illustrate a little bit today. And in terms of thinking about what might be a key enabler for you in order to get started, certainly the Green Chemistry Teaching and Learning Community, or GCTLC, that Beyond Benign launched a year or so ago now, is a fantastic place to get started. I strongly believe that this is the place to go to, where both for experienced practitioners and those just starting out, this is the place to go to be able to think about how can I be doing something more? How can I get started on my green chemistry journey to be able to think about moving my curriculum from here to here? There's a phenomenal number of fantastic resources, as you can see in the statistics on the right-hand side available, but there's also a phenomenal community as well for you to be able to meet and learn from others that might be either at a similar stage in their journey to yourselves or have walked the walk and are able to collaborate and mentor with you. So have a look at that QR code in the bottom right here and do sign up for the GCTLC. It's immensely useful. I'm on there and I look forward to networking with you in due course. So thinking about student partnership, how can we get these started to evoke change? I mean, I would strongly advocate, as I've mentioned, for signing the green chemistry commitment to get that initial license and buy-in top down from the university. That's been immensely powerful. But you can get started in other ways too. And certainly at a fundamental level, leveraging curriculum changes through having student representation on key committees, such as teaching committees, for example, where the students themselves are committed to integrating green chemistry into curricula, is a really powerful leader, as are student-led societies and associated ambassadors. And in order to make that change, whatever it might be, I'm going to give some examples in going forwards of how we've empowered the students to very much do something new to create a resource that might be available on the GCTLC, for example, for us to use with their peers and with future cohorts as an example of integrating green chemistry into curricula. So I'm going to go through some examples along those lines. And I'm also going to then go through some examples that, as well as making local change and helping us to transform our curriculum by integrating green chemistry, actually some broader sustainability advantages of some of the work that our students have done that have made real societal enhancement, particularly in less economically developed countries. So I'm going to go through some examples there, and then I'm going to bring it back to this coordinated effort and the impact of signing the green chemistry commitment in terms of how, through instructors that perhaps didn't even know what green chemistry was, now being on board with us, as in our case, an academic faculty 70 strong, where we're all working towards this goal. So that's what I'm going to try to do over the next 20, 25 minutes or so. And I'm going to start by actually talking about an example where we did work with students as partners, but this was before I knew what green chemistry was. So I didn't have any green chemistry instruction as part of my undergraduate curriculum, as part of my undergraduate degree program at all. When I was a PhD student, I didn't do any green chemistry. I happened to be making an actual polymeric material for targeted drug delivery. So based on the application, in that it was biomedical, I had to make, in hindsight now, probably lots of green considerations, but I didn't know what green chemistry was. When I first came to York about 10 years ago now, I wanted to integrate some materials chemistry into the labs, okay? And I thought Silly Putty would be a fantastic place to start. It's a really nice example when students make slime and flubber and have lots of fun by cross-linking effectively polyvinyl alcohol and borax. And we thought we could use this as an opportunity to teach students materials chemistry and teach students rheology. And indeed, that's what I did in a previous institution where I did my undergraduate. So you can see the flubber there, where we were able to investigate the shear thickening liquid there. So you could have a look at how the viscosity changed as you added more of a cross-linker. There's a gelation point and it gets really thick. You look at how it flows and everything else. And then I started at York and I thought, this is a great experiment. I'll make an impact as a new faculty member by integrating some materials chemistry into the practical laboratory. And then I met colleagues within the Green Chemistry Centre of Excellence, and they said, Glenn, we do not want to be using borax at all because of this H360 symbol, may damage fertility or the unborn child. And this was very much the catalyst for me to learning about what green chemistry was, okay? The fact that I thought I was doing something good, but upon taking this holistic systems-based approach and looking at all the components properly and not just thinking about what I wanted the students to learn, which was rheology, I actually learned about green chemistry, and we work with students as partners to investigate other systems. We did this through internships, through research projects. Initially, the gel that we made wasn't quite as impressive as Silly Putty, a very small amount, just using a trimetaphosphate, which has its own problems as a cross-linking agent. So what we ended up turning towards was effectively a seaweed-based system there. And you can see Brendan has actually used alginate in conjunction with calcium chloride. So we substituted this PVA borax system for a calcium chloride alginate-based system where you can get ionic cross-linking through the carboxyl moieties and the calcium cation. You can get the same learning objectives, so you can look at whether it's shear thinning, shear thickening, modulation. You can get actually some learning objectives through this greener route that we didn't anticipate. So you can look at disaggregation, for example, by adding trisodium citrate. And this was all led by students, all right? I wanted to do something, it was effectively blocked because of borax. And so actually I didn't have any funding at the time, but rather I worked with students as part of the curriculum that happened to be doing, I think it was a 6-week, 2 days a week undergraduate project with me in green chemistry, no, I think actually it was materials chemistry at the time, okay? And this is what they looked into, okay? And Brendan was one of the students that happened to lead this work. And so we implemented it into the curriculum. And then I wanted to think a little bit more about, okay, this is quite powerful now. Can we link it to our research in the department? And can we try to solve some problems along the way? And so I was lucky enough to go to Brazil back in 2016, I think. And Brazil are one of the largest exporters of oranges in the world. And of course, when we all enjoy an orange, we peel it and we obviously eat the actual orange, but where does the peel go? Typically in the trash, in the bin, in landfill. But actually we can valorize this, okay? We can get valuable chemicals from this peel that we can use to transform into new products, okay? Linking to the responsible consumption production UNSDG related to a circular economy. So what we did was we developed a laboratory experiment in York to start with, where the students, through a benign process, extracted a pectin-based mixture, okay? And in combination with simply sugar, they can make jams. And jams are effectively gels, aren't they? And so they could do exactly the same studies to hit exactly the same learning objectives while making a usable product. We've also implemented this with high schools in the UK and in Brazil. So we are empowering our students to act like Paddington Bear and get value from this waste orange peel by making jams a new product that they can subsequently enjoy, okay? So this doesn't have to be all based in higher education. Some really nice high school applications as well. And quite nicely, our students, Lucy, Helen, Robert, all undergraduate students doing work as part of the curriculum, were able to publish this work. So it's great for their employability as well. It's another lab experiment for us to be able to use. And we're trying to solve a societal problem here, a societal issue, okay? That's the key. We got quite excited by this and we wanted to slowly empower students to do more and more in this regard. And so this time we had Mark, Connor and Catherine, UK students, collaborating with Gabrielle and Gabriella, Brazilian students, to think about a different waste stream. And this was sour milk. Okay, milk's gone off in your fridge. Can't drink it. I don't like to drink it. What do we typically do? We pour it down the sink, typically. However, again, using benign processes, simply lemon juice and heat, and some cookie cutters and coloring dye, we can make ornamental bioplastics. Okay, this is a really nice outreach experiment that you can do. We punched holes in them, and with string, you can make Christmas decorations if you celebrate Christmas. So it's a nice thing to do this time of year. And in doing so, we are aligning with a UNSDG around circularity. But by using a whole systems-based approach, we learned that our friends in India depend on this type of approach for nourishment to make paneer cheese, and in doing so, addressing a different UNSDG, okay? And so this enables us to teach about ethics. Okay, so just because we can do certain chemistries, perhaps those certain chemistries may be greener. Okay, should we? Yeah. So that was one thing, again, that our students developed through partnership with other students elsewhere on a different continent. This was quite a fun project. This was with a team in Peru, and my student at the time, Kishan, he did a year-long master's project with me. Okay, Kishan didn't. He won't mind me saying, didn't like chemistry quite so much, but he loved engineering. So I was thinking, okay, what sort of project are we going to do here? And what Kishan identified is that in the mountainous regions in Peru, access to clean drinking water, water to sanitation, for sanitation, is particularly scarce. Okay, but there can be a lot of fog. Okay, and what the local communities did about that at the time is they had these that I've tried to depict here, fog catchers. Okay. And so effectively what happens, the fog comes into contact with the fog catcher, and through condensation, water is collected at the base there, which can then subsequently be upcycled. Okay. And originally I was just thinking about, okay, how can we use this as a fun demonstration, practical for teaching purposes? And we were able to replicate that. You know, I asked Kishan to have a look at the materials and also the shape and the design of the fog catchers. And what he found was, actually, as you can see with these fog catchers, okay, it's sort of like a cross stitch in terms of what the net looks like. What that meant is water droplets were clogging into the corners, so they weren't all filtering down into the collection. They were being stuck. And so Kishan had the idea of using simply a harp, okay, so just vertical components, as you can see here, and therefore there's no corners for the water droplets to stick in. And he was able to see that the efficacy of this fog catcher was so much greater at the scale that he was doing it at compared to a kind of cross stitch mechanism. So that's great. But what it subsequently led to is the students and ourselves working with communities in Peru to redesign their fog catchers to be a more harp-based system to capture more water, okay, as opposed to the cross-stitch. So originally this was just an educational intervention that's really led to this exciting community project, okay? There's other examples. I'm not going to go into this too much detail because I want to talk about things at the departmental level. But as you can see, again, examples that have been led by our students that are doing research projects with us in green chemistry, but oriented towards transferability to make an educational resource for us. That's a big model that I apply in my own research. Okay, and in this example here, Lauren really loved coffee. And so Lauren decided to, again on the waste valorization theme, approach all of the coffee shops on campus and to collect all of their spent coffee grounds, okay, after they've made coffee, to be able to upcycle them and make biodiesel derivatives, okay, and make a laboratory experiment around that, okay. So it's a model that works really well for us. I'm going to go into a little bit more detail on this example here before moving on. And it might be something that you wish to consider. I mean, it might be the case that you just want something really good that you want to implement with your students that's easily transferable, cheap reagents, doesn't use crazy instrumentation, but teaches certain principles and meets certain learning objectives. And the GCTLC is the place to go to be able to do that. But if you want to try and develop your own, okay, I'd encourage you to have a go. And these are the types of projects and models at which I've had experience with. A lot of the time, you know, I mentioned I'm a materials chemist by training. Yeah, I just know how to make gels. But actually, through working with students and following their interests, we've been able to conjure up a few pretty good resources, I think. And this is another example that Oliver did. Again, what I told Oliver, he was working with me for about 9 months or so, 5 days a week, 4.5. And effectively, I said, Oliver, we've developed this cool solvent called Cyrene as a replacement for N-methylpyrrolidinone. Make an undergraduate experiment based on this that's linked to pharma, something exciting. Off you go. Was actually where I left it. And Oliver found something that meant something to him, and looked at this traditional synthesis of something called bupropion hydrochloride, okay, an antidepressant and smoking cessation aid. And you can see the traditional synthesis on the top there, okay, using dibromine in conjunction with DCM, which is banned just now, NMP, generating quite a lot of waste. And you can see how he greened it by using this route. He made it greener, okay? And really, all I say to Oliver and a lot of my students that embark on these sorts of tasks is follow the green metrics as you go. Whenever you make an intervention, I want you to see quantitatively the impact that it's actually making, okay? And certainly PMI is something that we look at very closely, okay? You may also wish to look at the dozen tool as well from Miller-Post Sigma. So there were lots of issues with this synthesis. So I got Oliver to reproduce it to start with, get your experimental technique, tell me about the issues, let's prioritize how we're going to address them, okay? I'm not going to go into this in lots of detail, but all I just want to illustrate is the process at which Oliver went from looking at the traditional synthesis there, seeing what the PMI was, breaking it down to give us a steer as to where we should be focusing our efforts. So, for example, the extraction here. And then making changes. I say I'm not going to go into chemistry as really as part of this presentation, but making changes and showing me the evidence for how you've been able to make the reaction greener. Okay, and you can see pleasingly the PMI is going down with the various iterations that Oliver made. What, interestingly, I think we decided at the end was thinking about, that was that dibromine that I showed you in the traditional synthesis. We decided to move to N-bromosuccinimide. Okay, now if you think of where NBS actually comes from, it probably isn't a greener substitution. Okay, it's as bad, if not worse. But actually, we decided to move towards it, even though if you see the PMI has gone up ever so slightly. Okay, gone from 46 to 47. So why did you do that, Glenn? Again, that's about systems thinking. It's a lot nicer and safer, I would argue, for students to handle NBS in the labs compared to dibromine, okay? So it's about thinking of the wider picture. And so that's where we ended up with this particular synthesis here. I'll go quickly through this one because I want to talk about the coordinated effort, but we have worked with students as well to develop resources in partnership outside of the lab, okay? So this one is something called the biorefinery experience, where we work closely with some colleagues in Brazil to get information about a sugarcane biorefinery, okay? And to be able to make an interactive resource where we could teach undergraduate students about green chemistry using this case study, okay? And so, yeah, that's the actual link there, should you wish to have a look at this free system and this free website. And really, this was all about introducing quite a high level kind of what systems thinking is. I'm not going to talk about these sorts of maps, but systems-oriented concept map extensions are something really popular in the community at the moment in terms of visualizing the interconnectivity between systems. Though if you, from a cognitive overload perspective, it does look a little bit scary, particularly this one. But what we tried to do with this model, which was new, is with this website that was new, is to develop this new model that tries to facilitate dynamic problem solving. So what we tried to do was, using real data, we got students through an interactive Excel sheet to design their own biorefinery in the optimal way. Okay. So they did that here. And that was to represent the present. Okay. And then we perturbed the system. Okay. We did a climate change scenario in however many years. And the students had to understand this new system. Okay. And think about how to optimize the model given these parameters had completely changed. Okay, so we tried to facilitate dynamic problem solving there. This was all led by the student, really. Okay, I actually do very little work as part of these projects. It's all student led. I just act as an advisor. Okay, and I'm going to skip this part, but this was just saying we evaluated it and it was hopefully useful. And I'm going to just talk a little bit about some more individual resources before talking about this departmental effort, where we've been able to transform the examples that I'm doing now to something much more coordinated. As I say, non-lab based resources I'm really interested in as well. Games, for example, okay? So here we wanted to use systems thinking to make a card game, okay? So here's the board. A student working with me for 1 year made this. And effectively, you've got to be the first to compete against others to launch a recycling plant, be it paper, plastic, glass, metal, food. So you have to understand your own system. So you pick recycling plastic by collecting cards, okay, such that your strategy that you employ helps you to win. You have to understand your system, but you have to understand the other systems as well, so you can make it more difficult for your opponents, okay? And so you can see students in the UK at the top there, in the US. We did this in Morocco for the first green chemistry training school last year. These are the cards. You've got waste plastic, that's your feedstock card. You've got instrument cards there in terms of machines, a molder, okay? And also we have these purple cards that try to facilitate that dynamic problem solving, power cut, drought, flood, etc. Okay. We've also again worked with students. Matt was really interested in games, but online games. So he made an app called Green Tycoon to teach green chemistry. And then I thought, well, as opposed to making new apps from scratch, can we use existing apps like social media to be able to share the green chemistry message? So I did a little bit of work on this using a photo messaging app called Snapchat, but then I realized, well, why not transfer some of the work to our students and empower them, where they have now made a TikTok channel, for example, to communicate and share green chemistry. And so you can see here an example of one of the videos that they made. So that's all very well, but there is a problem, as I've tried to allude to. This works well with Glenn working with students as partners. Okay, there's me on my phone doing social media, and you have students in the background. But I'm only one person, and that makes it really difficult to evoke change. As much as I love working with students as partners, as much as I love developing new green chemistry education resources and sharing them as effectively as I can, as much as I love doing that, the impact collectively on the whole degree program for our students, I would argue, could be better. And so this is where signing the green chemistry commitment for us, and we are in the early days, we signed about 1.5 to 2 years ago, has already had a huge impact on our department. So for example, Caroline, our head of department, has extremely strong buy-in, and in terms of the workload allocation for academic staff, for administrative staff, for technical staff, ensures that there is time within everyone's workload model, love it or hate that phrase, to be able to work to integrate green chemistry into curricula. That's the brilliant thing about the green chemistry commitment, is it needs that higher level sign off by a dean, a pro vice chancellor, in conjunction with the head of department, so that this becomes a priority and this happens. Ian Fairlam is a world-leading researcher in inorganic catalysis, and part of his work is using metals of higher abundance to be able to facilitate catalysis. Okay, and he, upon signing the green chemistry commitment, now integrates a lot of that research into his instruction. So we're not looking just at using elements with low natural abundance, palladium group metals, for example. Dave is our organic teaching subgroup lead. So he curates meetings for us multiple times a year to holistically look at our organic chemistry curriculum. And there's about 15 instructors, and one of them, that feed into that, where through all of our courses, we are highlighting traditional methods. We think that's still important, but greener alternatives as well to facilitate various reactions. Liana works in our structural biology unit, and she has been teaching the students now about toxicity. Okay. Again, we would not have done this without signing the green chemistry commitment. It's at an early stage, but we're building on it. David is our teaching-based focused member of academic staff working in laboratories. He now has a mandate to ensure that the experiments that students do that might not be green, for example, at least they're looking at the metrics and the implications of it beyond yield, atom economy, but they're looking at PMI. They're using the dozen tool, and he is ensuring that the lab is, that all labs are now compliant with legislation. Avtar runs, in conjunction with Tom, our postgraduate taught program, or MSc in green chemistry, which was the first in the world to be created. He has a work stream on decolonizing the curriculum, whereby he uses Matharu plots to get students to think about the literature at which they are using when writing up a review or a report, and thinking about where it originates from in the world, be it the global south or the global north, why that's the case. Saranjana is a technician within our department and has been strongly committed to training our students to operate much more sustainably in the research labs, for example, okay, and when they prepare samples for analysis. Matthew is our deputy head of faculty operations that works on the student experience. And so while he isn't an academic focused on the green chemistry side of things, he's been prompted to think about how he may streamline administrative processes such that we can work with more agility, efficiently, and sustainably in alignment with our net zero goals as a department and university. So really, the green chemistry commitment has helped us transition towards one or two, and you're lucky, I think, in a department if you are more than one. I'm in a very privileged position, I realize, but transitioning more than one or two or three members of staff that are luminaries in green chemistry and want to enlighten people and doing good work in different areas to a collective effort. Okay, that for me has been the power of the green chemistry commitment in York Chemistry. So a coordinated effort to infuse it into curriculum. And I believe that these new and more effective staff and student partnerships, and we are still emerging, you know, obviously I had a lot to talk about in terms of my own work, the coordinated stuff, the wheels are moving, and I hope to be able to update you in the future as to how, as a collective, this really is becoming, and hopefully will be, transformative for the chemistry offering that we are facilitating at undergraduate and postgraduate levels. So I've tried to talk about the approach that I use, this systems thinking, very briefly. Very much trying to enact change through partnership, through my journey as not knowing what green chemistry was, yeah, coming into York and saying, Glenn, no, you can't do it this way. You need to learn, do it another way. Yeah? Coming from that to where we are now, thanks to Beyond Benign, moving away from an individual spearhead to a collective harpoon. And as I've mentioned, the Green Chemistry Teaching and Learning Community, the GCTLC, is the place to go to get started, but also develop what you're doing to a higher level. It's a fantastic networking place, and I really hope to be able to see and meet more of you on that platform. Thank you.
All right, Glenn, thank you so much. That was beautiful. And also, like, not only in terms of systems thinking, like parameters, but also in terms of systems thinking, like going globally and helping like people in different places to show like what the good they can do and the resources they can use. So this is amazing. Thank you so much for this. Thank you for being here. I'm just gonna briefly, if my technology helps, um, like just share a little bit of how you can participate of the green chemistry commitment, and then we can go for the Q&A period. So hopefully you can see my screen in a way that works. But as Glenn said, the green chemistry commitment is this collective voice to empower the community to practice green chemistry. So you're not the only one, but part of this network is a commitment to continue improvement. So you don't have to be perfect in your implementation of green chemistry to participate. You just need to have this idea, this intention to keep going. Is a volunteer and diverse program, and actually the idea is to inspire other faculty and also your students to start doing and practicing green chemistry. So as the institutions, they commit to start their green chemistry journeys, at Beyond Benign, we commit to support you in terms of different strategies. They can be professional development, grants, or also increase the visibility of what you're doing in your department. And also, each institution does what works for them. We're never going to say what you should be doing because we understand that different people and different institutions, they have different resources. So our goal is to help you. And also you can learn more about this, what others are doing in the case studies that we have, and also in the paper that we recently published at the Green Chemistry Journal, and I'm going to make sure to send all of these to you. So in terms of the impact, you can see here there's a map of all of the green chemistry commitment signers around the world. Today we have more than 20 countries in the world participating in this program, and we estimate that we're reaching over 4,000 faculty and 1 million students per year throughout the program. And today we actually have 198 GCC signers throughout the world. Since we're talking about a lot of students, I just wanted to highlight some opportunities that we have for students. The students in the Green Chemistry Commitment, they can also serve as community ambassadors and talk about the program, and also about Beyond Benign to their peers and colleagues. And we also have an event that happens every month, which are the Green Chemistry Connections. And we also have an amazing group of students helping to organize and promote this event. So in terms of the green chemistry commitment, if you want to participate, I'm going to send you after this this webinar some documents. So basically, we just need you to tell us which department you're coming from and the institution. And also, as Glenn mentioned, the commitment needs to be signed by the departmental chair and also one administrator. And then basically your institution joins the commitment. And also we also request the primary contact, which is going to be the champion or the liaison between the Green Chemistry Commitment Program and your institution. And you can send those to us. Also, if you want to learn more about how joining the Green Chemistry Commitment, there's a QR code over here. It's going to take you to an agenda so you can book a meeting with me and we can discuss how to make this possible in your institution. Or if you're a Green Chemistry Commitment signer and just wants to talk, we can do that as well. So in terms of the green chemistry commitment, any institution that teaches green chemistry can participate. There are no fees or costs associated with the program. We work to support you, and also it's a diverse and non-prescriptive commitment to continue improvement. You don't have to be perfect to join us. And also, as Glenn mentioned, please join us at the GCTLC Green Chemistry Teaching and Learning Community so we can continue this discussion and make sure you're all supported and you have the energy to continue this transformation. So with that, I'm gonna thank you all. This is another QR code that's gonna take you to our newsletter. And I'm gonna stop talking and let you ask Glenn all of your questions. I see a lot of nice comments in the chat, Glenn. People are super thankful for your presentation. But we also have a question from Ronnie. And they're asking how hard is it to get approval to do research with your students as subjects, and are there significant RRB restrictions?
Yeah, great question. Okay, certainly in terms of working with students as partners to develop new resources, be it in the lab or non-lab based, absolutely not. However, I don't think that's your question. It's more about evaluating the efficacy, I think is what you're asking. And yes, we do have to go through ethical approval. It tends to be pretty facile from my perspective. I don't think it's ever been rejected. I think it's important that students aren't disadvantaged relative to others. So, for example, it might be that you may think a clear control group might be helpful in actually splitting the same cohort up into two, whereby half may be given a resource and half not, and then evaluating learning gain. I think that probably is unethical. But it hasn't been a stumbling point for me, I would say, broadly. And I think that there are still useful mechanisms that allow you to evaluate whether you've made something that's helpful or not without causing those issues. Thinking about ethics early is something that I would advise. I think, if anything, the challenges that I have is we do tend to make quite a lot of things as in green chemistry education resources, and in order to publish them, of course, we want to know for ourselves. You have to demonstrate their efficacy, and sometimes the technicians and the lab coordinators tear their hair out because I've got another 3 experiments that need trialing, and so collaboration has been really helpful for me, and I'm certainly open to expanding that pool of collaborators that might want to try something new within their curriculum to see how it works. I think it can only act to enhance the piece as a whole and the story as a whole if you can demonstrate it being effective, for example, in multiple environments, multiple countries, perhaps. So, if anything, the problems that I have are very much about finding others to be able to trial some of the things that we make. Yeah.
Awesome. Thank you, Glenn. We have Safayat. Please let me know if I pronounce your name correctly, but they would love to know about funding or opportunities and open graduate research positions for your department. So I can put you in contact with them. That sounds okay.
Yeah, absolutely. Yeah. Funding opportunities. I think in general, what I tried to describe was that much of the work has actually been done by students as part of their degree program. So I think that's quite a powerful lever as well. And it's making sure to the faculty, and when you're doing the assessment, that actually this is chemistry. It's oriented towards chemistry education, but they are doing real chemistry here. Not that chemistry education isn't real chemistry, but yeah. So I think that's powerful and allows you to do it without a lot of money. Obviously, there's little internships as well. In terms of working with us more broadly, please feel free to get in touch with me, and I'll do what I can. I'm always open to exciting discussions with people that want to get involved with green chemistry education.
Awesome. So we're at the hour. I just want to let you know, in terms of questions, you can always reach out to Glenn in the Green Chemistry Teaching and Learning community and talk to him. He's over there talking to all of the people. We also have a question from Arbir regarding collaborations. So Glenn, you have a lot of a lot of things to catch up. But I just wanted to say thank you so much for being here at this Green Chemistry Commitment Info session. Glenn, thank you so much for sharing your expertise and all of the amazing things you do with us. We're just super honored and happy to have you. And we're looking forward to the next one. So thank you so much.
Thank you.
Thank you, everyone. Bye.